About me. So first thing I should say is it's not quite Dr. Ben yet. Still got a little while longer to the PhD, but we'll get there. Okay, so almost Dr. Ben is who I am today. What I'm gonna do is tell you about some of what we already know, some of what we don't know about black holes and dark matter. I'm gonna hopefully get into some of the really recent work, some of the things that I've been working on, and here's the plan for the evening. I'm gonna start out by giving you guys some background on what dark matter is, what black holes are, and then I'm hoping we can spend some time digging into the connections, some of the really recent work. But that said, I'm really hoping this can be an interactive kind of back and forth. Let's make it a discussion. So as I'm going through, if you have a question, if something comes to mind, or something doesn't seem quite clear to you, shout it out. I want to hear it. You can raise your hand if you feel more comfortable. I'm totally okay with us taking a tangent, and if we don't get to everything I wanted to talk about, that's okay, all right? Okay, so you guys are driving the evening. You're gonna work with me here. Okay, so we gotta start somewhere, and if there's some place to start talking about dark matter, a good place would be about 1 million light years away from the Milky Way galaxy. So let's start here, and let's start with the following observation. Everything has a gravitational pull, right? Doesn't matter what. So that's one way for us to tell how much stuff there is in a galaxy like this. Now there's one problem. If you do this, if you measure how much stuff there is in our galaxy, and then you actually go and add up all the stars and gas and dust and everything else that we see, that stuff is only 20% of what we know is there. The rest? Something invisible. We don't know what it is. We just call it dark matter. We know it doesn't emit light, doesn't reflect light, doesn't seem to bump into us. Now, okay, I'm a physicist. This is very embarrassing. Because we spent the last century here. We spent millions of dollars trying to figure out what the universe is made of, and we apparently have missed 80% of it. So that's a problem. Now, in case this isn't enough motivation to figure out what this missing 80% is, let me give you one more pragmatic reason why you might want to know about dark matter. And let's do that. Let's go back to electricity. All right? We've known about electricity for thousands of years, actually. The Greeks knew about electricity. And just a few hundred years ago, we figured out how to harness it for our own benefit. But it wasn't until a little more recently, just around the turn of the century, around 1900, that we actually discovered what electricity is. Now, I have a device over here. It's a device of a class called electronics. Now, why do we call them electronics and not electrics? Why? Why do we call them that?
Electrons flowing?
Electrons flowing, thank you. So it's not just about electricity in bulk. We already knew about that. But it was around the turn of the century that we actually discovered that electricity is the flow of electrons, actual particles that make up this electricity. So there was this fellow, J.J. Thomson, and his group. They discovered this new particle. And they didn't know in 1900 or so that discovering the electron was going to usher in an entire new age, a new step in civilization. All right? So likewise, we have this mysterious matter. We have no idea what it is. And if you're looking 100 years down the road, we have no idea what kind of future that stuff could enable. So I want you to keep that in mind as we go through this, and as we try to delve into what this missing matter is made of. All right? All right, now let's go through just a little bit of the history. Why do we actually know that there's this 80% that's missing? So this goes back to a Swiss astronomer by the name of Fritz Zwicky back in the 1930s. He was observing a cluster of galaxies. Every little splotch in the screen is a whole galaxy. And he was doing some math about how these galaxies should move, and he noticed that there was something wrong. When he came up with the answer at the end of the day, they were just moving completely wrong. It was as if there was something else tugging on them, something that he couldn't see in his telescope. And so he had the idea, maybe there's some extra stuff that you can't see, that just isn't showing up in the telescope. Maybe it's dust, maybe it's some kind of weird gas, who knows, we can't see it. And that was kind of in everybody's like, okay, I guess I know about that observation for a while. People didn't think too much of it. Now I want to flash forward a few decades, and this astronomer by the name of Vera Rubin was measuring stars in galaxies. So this is one galaxy here. This galaxy is spinning around in this direction. Now, if something's spinning around, rotating around, something's got a pull on it to keep it moving in a circle. And you guys actually, you guys all know about this, right? Have you ever taken like a ball on a string and you've ever swung it around? So you know that to keep this thing moving in a circle, I've got to keep on applying some force to it, right? Now, if I want to make it move faster, like that, it takes more force. I've got to pull on it harder. Yes, this is my cat's toy, and she was very disappointed when I stole it from her this morning.
Is that clockwise or counterclockwise?
This particular galaxy is rotating like this here.
Clockwise.
Yeah, clockwise. So here's the thing. Vera Rubin went and actually made these measurements. How fast are the stars moving? And therefore, how much force must be pulling on them as they go around? And what she found was, if you only had the gas and the stars and everything you can see, you would expect this line, as you go out towards the edge of the galaxy, things shouldn't be moving around so fast. Instead, the data are these points over here. The only way to explain that, the only way to get that extra force, is if you have a lot more mass, a lot more gravity pulling those stars around in a circle. So this was a big piece of evidence that started us thinking, maybe our picture of the universe is really incomplete. Okay, now I do have to address one point that keeps on coming up in the news, and that's that we have only ever seen dark matter through its gravitational forces. And you might think, well, maybe it's not extra matter. Maybe we just don't understand gravity too well. What if there's just, gravity works differently in big galaxies? Who knows? Well, there are some people who think that this is the case, but most scientists think, in fact, it cannot be just a different kind of gravitational force. And there are lots of reasons that we think that, but I'm just going to show you one classic example, okay? Here's the picture. This is actually two clusters of galaxies. We call this the bullet cluster for reasons that will become clear in a minute. So there's two clusters of galaxies. They actually collided. They ran into one another, and they just kept on moving through, right? Now, this red region here, this is all the gas that rammed into itself and just stayed here in the middle. The blue, that's a computer filling in where all the matter is based on our measurements of gravity. So what you're seeing here is the gas got stuck and stayed in the middle, but most of the matter kept going. Now, if this were just some kind of modified gravity, if it were just the gas has different gravity somehow, you would expect most of the matter is here where the gas is. That's not what we see. This picture tells us there's some actual matter that we're missing here. Okay, so with that said, I have to point out, since all those observations that I talked about, we have done a tremendous amount of amazing precision work in how we actually understand the universe around us, and we've gotten a ton of data about how the universe has evolved over time, how dark matter has played a role in that. I don't think I have time to really go into these plots in a lot of detail, but we can actually measure things like how much dark matter there is to like 1%. We've gotten really good at this. Now, we can also look at dark matter in the form of computer simulations. So I want to show you a picture from one of those simulations, and it's showing up a little funny on the computer screen, but everything you see in this picture is just dark matter. We put dark matter in a computer, we let it go. We just let it clump up and gravitate. And what you're seeing here, these bright spots, that's where dark matter has gotten really dense. It's made these clouds of dark matter. And those are actually the places where galaxies form. What we've actually learned from this picture is dark matter has played such an important role in the history of the universe that we wouldn't be here without it. If there weren't dark matter around, forming these clumps, pulling in gas, starting off galaxies wouldn't have formed. So now I hope I have your attention on why dark matter is something we ought to be interested in. Now, part of what we can do with dark matter is understand the history of the universe in more detail. So this picture, it was drawn once by I think somebody at NASA, and it's been used by so many of us. So I shouldn't claim that I've drawn this, but this is a brief picture of the history of the universe, all the way back from the Big Bang to the present day. Now, what we think is, in the very first moments of the universe, there was a period of extremely rapid expansion. The universe inflated, and then about 400,000 years after that, there's this light that was left over, this kind of afterglow that we can still see today. We call it the cosmic microwave background. Then, after a few 100 million years, stars began to form. We start seeing light from those very early stars. We start seeing galaxies. And now, all the way to the present day, we have galaxies and clusters. We can see this structure that's formed on cosmic scales. And what I want to point out is all of this, at least from here on out, is actually visible to us today. Because light takes time to travel to us, we can look at things that are very, very, very far away, and that corresponds to looking at things that happened a very long time ago. So we can actually see light from this almost this entire picture. And we can actually test our model for how the universe has changed over time. Okay, now, what is our universe made of? Just to break it down for you, you and me and everything else we see, we are this purple sliver in the pie. We're about 5% of everything that's in the universe. This big yellow chunk, this is something we call dark energy. We're not going to have too much time to go into it this evening, but it controls how quickly the universe is expanding right now. And the rest, this green part of the pie, in some sense the one we understand the least, is dark matter. Okay, now what I want to do is just recap a couple of the things that we do not know about our universe. We don't really understand what happened in the very first moments after the Big Bang. We don't have a great understanding of physics around the time of inflation. And it's just because we can't really experimentally probe it. It's very hard to see. So we have some theories, it's very hard to test them. We don't quite understand why we have matter today. And when I say matter, I'm not talking about stuff in general. I really mean matter. Because you might think there's matter, there's also antimatter. Why didn't the universe just make a bunch of matter and a bunch of antimatter and collide them together and poof, everything's gone? Why is there matter left over today? That's still something that we don't fully understand. And finally, we have no idea what dark matter is actually made of. So to answer at least this third question, that's going to be our focus for today, I want to turn for a moment to particle physics. All right? This little diagram here, this represents all the particles that we know about. It's kind of a periodic table of particle physics. And this set of particles is actually, it's an incredible model. It describes everything from atoms to molecules to you and me, to Earth, to the sun, to stars. Basically everything in the universe that we can see is made of these particles in this little diagram. It's a pretty good model. Of course, the one thing that it doesn't seem to explain for us is what dark matter actually is. So, the idea here, one of our best guesses about what dark matter could be, is a new particle. Something that doesn't fit into this picture. That might seem a kind of a radical idea. Like, why should I invent a new particle? Like, am I just, making up excuses for why we don't have this dark matter? And what I want to just provide you with as some context is that adding a new particle like this isn't really that weird. And the reason I say that is we already know of particles in this model that behave almost exactly like dark matter. And I'm talking particularly about neutrinos. So what's a neutrino? A neutrino is a ghostly kind of particle that doesn't really like to bump into anything. Doesn't emit light, doesn't reflect light. It just kind of zips through everything. It behaves in almost every respect exactly like dark matter. In fact, we thought for a while neutrinos could be dark matter. We realized there are other problems with that. But all these weird properties of dark matter are not so strange from a particle physics point of view. We see neutrinos coming out of, say, nuclear decays. When atoms decay, they emit these neutrinos. And they are so ghostly and elusive that, let's imagine we tried to block a neutrino. Okay, I'm going to put up a wall and say, I want to stop a neutrino from coming. How much lead do I need to stop a neutrino? Actually, any guesses? Anyone want to take a guess? How much lead do I need?
Several feet.
Several feet?
3 light years.
Okay, that's about the right order of magnitude. Yeah. So yeah, if you go to the doctor's office, there's an X-ray machine. You want to be behind a little bit of lead to protect yourself from the X-rays. Okay, yeah, a few inches might do it. For neutrinos, we're talking about light years of lead to block neutrinos. Yeah.
Haven't they been able to stop a few?
Okay, so how have we actually been able to see them, right? Yeah. So that's a really good question, and the answer is because there are so many of them. The sun is constantly bombarding us with neutrinos. There are just hundreds of thousands going through your body right at this very moment. So every now and then we get really, really lucky, and one bumps into a particle in one of our detectors, and then we can see it. So the detectors that we use for this are actually, they're enormous. They're these water tanks that are just gigantic. You can take a boat inside them. And even one of those gigantic detectors will only see maybe 5 or 10 a day if we're really lucky. So yeah, they like to go through things. So with all that in mind, it's not so crazy to imagine that maybe we have some extra new particle that fits onto our standard model of particle physics and completes it, explains dark matter. Now, if we have a new particle like that, well, we got to go look for it, right? And we have tools for doing that. We've discovered a lot of particles in the past using particle colliders, like the LHC, right? We smash particles together, see what comes out. You might think if we have a new particle, like dark matter, maybe we can make it in the LHC. So this is one way that we look for dark matter. Another way that we look for dark matter is by building giant particle detectors like this one. And here the idea is, if we're really lucky, one of the dark matter particles from space happens to wander through our detector, bumps into something in the detector, shoots off some electrons, and we see it. All right, so we've been doing both of these things for quite some time. Let me show you what we found. Yeah, nothing yet. So in this null result, in light of what I've told you so far, you might be questioning some of the basics. You might be thinking, well, maybe dark matter isn't a new particle after all. Maybe there's something fundamentally wrong with how we're doing this. But I want to put this in a bigger context, a much bigger context. This line here, this is showing the different masses that are possible for a dark matter particle. And every tick on this axis is a factor of 10, except for this tick, which is 40 factors of 10. So this is a huge range. Dark matter particles could be anywhere in that range, and we've pretty much only looked for it here under this lamppost. Now there were good reasons for us to start looking there. We had good theoretical reasons to expect dark matter should be there, and it's easy to look for it there. We're going to look for it there first. We haven't found it there. It could still be there, but now we're starting to broaden our search, and we're thinking about dark matter of very different kinds. Dark matter that's very, very light, for example. Here, at this end, dark matter is so light, if you think about particles and waves, right? A particle is a kind of a wave, and it has a wavelength. At this end, the wavelength of dark matter particles is as big as galaxies. On the other hand, all the way up here, one dark matter particle has the same mass as our sun. Could be. We'll get to that. So really, the problem is, if we want to look for dark matter, well, it's kind of hard for us to look everywhere in this range. It's enormous. It's just too big. So we would like to find some way of learning about dark matter, even if we can't just get one particle by itself in a detector. And we do have one tool to do that with, and that's gravity. Gravity is really special among the forces. Why is that? First of all, it's universal. When I say it's universal, I mean everything feels it. Everything has a gravitational pull. Everything moves under the force of gravity. We'll look at why in just a little bit. But that's step one. Dark matter feels gravity. Step two, gravity is very, very weak. And why do I say it's weak? Well, let me give you an example. I picked this up, right? I pulled against the gravity of the entire Earth. And yet I, with my little arm here, didn't have any trouble doing that. So gravity, compared to other forces, is just so weak that that's actually why we've only been able to see dark matter on cosmological scales, in galaxies. The reason is, if we have one dark matter particle that comes through our detector, well, okay, we're not going to feel gravity from one tiny particle. Gravity's too weak for that. So we'd like to be able to learn more about dark matter using gravity because we know we can. We know dark matter feels gravity. We know dark matter pulls with gravity. The problem is, we got to get over this fact of gravity being weak. So we got to find some place where there's a lot of gravity. really strong gravity. Anyone have any ideas where we could find some strong gravity? Okay, I'm hearing lots of great answers. Stars, neutron stars, black holes, the sun. These are all excellent answers. In fact, all of these are things that we've explored as ways of getting at dark matter. The one that we're going to focus on tonight, as you might have guessed from the title, is black holes. And by the way, as long as I have this picture on the screen, I have to just say a word about it. This is actually a screenshot from Interstellar. And you know, usually when movies do black holes, they get just everything completely wrong. And Interstellar was really refreshing because you know the guy that they got to do the scientific consulting for this movie? That guy was Kip Thorne. He's a Nobel laureate. He's one of the world experts on black holes and gravitational waves. And he advised them on, among other things, this image. So this is actually a scientifically realistic image of what a black hole would look like, but made with a Hollywood budget. So I get really excited looking at this. All right, but yes, if you're looking for really strong gravity and you want to learn about dark matter, a black hole is a natural place to do it. So now, I want to switch gears a little bit. Let's talk a little more about black holes. Before we do that, we do have to learn a little more about gravity. So let's take a look at how gravity behaves in its most extreme incarnations. So you might have learned at one point about Newtonian gravity. Isaac Newton, back in the 18th century, laid out the rules for how gravity works as a force. But then there was this fella in the early 20th century by the name of Albert Einstein who came along and said, actually, you're completely wrong. Here's how gravity works. And we call this the theory of general relativity. So what is general relativity? How is it different from Newtonian gravity? Well, the idea in general relativity is that gravity isn't actually a force at all. Instead, it's curvature of space-time. And we draw pictures like this to try to convey that in cartoon form. So in this picture, the idea is you have a star or something heavy sitting in the middle, bending space-time around it. And then if we have a planet orbiting the star, it's kind of like it's just circling around in this little well that the planet has made, or the star has made. This is actually a terrible, terrible picture. Okay? I wish we had never started drawing cartoons like this, but now everybody's used to them. So I want to give you a slightly better picture of what general relativity is saying. And before I do that, you can tell something's wrong with this picture because what's pulling the planet as it goes around? Like, there's no gravity this way, if gravity is the curvature of space-time. What's pulling everything down? So let's take a slightly different picture, okay? Here, let's pretend this is a globe, okay? This is the Earth. We've got the equator here. And let's put two people, A and B, on the equator. Separate them by a little bit, maybe 20 kilometers is in the picture. Now let's say that both A and B start walking north, okay? So A is over here, walking north. B is over here, walking north. They're walking in parallel directions. Now parallel lines, do they intersect? Yes or no?
No.
No, parallel lines do not intersect. Well, they don't intersect in Euclidean space. But this space is curved. So if we follow A and B as they walk forward, as they walk due north, they will eventually meet up at the North Pole. And A says to B, how'd you get here? I just kept on going straight. And B says, how'd you get here? I just kept on going straight. So the answer is, because this surface is curved, straight for B and straight for A brought them closer together, even though they were on parallel paths. Now, why is this related to gravity? I want you to think about north as corresponding to forward in time, and east and west corresponding to space. So like space is a line here, and as it moves forward in time, as we move forward in time, A and B get closer and closer together. The upshot of this picture is gravity is fundamentally the curvature of space and time together. So that by moving forward in time, our separation in space can also change. That is the key idea behind relativity, and it's what we're going to need to understand black holes. Everyone good with that? Look at you guys. You just mastered graduate level physics in 5 minutes. All right, so let's move on to black holes. So what's a black hole? Now the idea here, you may have heard things like it's something with gravity so strong that light can't escape. And in a sense, that's true. But let's think about it now in terms of curvature, in terms of geometry, because that's what general relativity is all about. So here the idea is a black hole has so much mass in so little space, it curves space so much that it forms this thing called an event horizon. An event horizon is kind of like a boundary in space-time. It's a one-way valve. Once you go past the event horizon, you can't come back out. Now what does that mean geometrically? Really what it means is, once you're past the event horizon, every direction that leads you forward in time leads you further in. You can't leave the event horizon. That would be like going back in time. So yeah, okay, light can't escape, but really you should think about this not as being something about like how fast you can go. It's really about what space is actually doing, right? It's the curvature of space-time itself. So understanding that we have this event horizon that we can't get out of, that's one thing I want you guys to hang on to. We're going to come back to that, okay?
But
All right.
That's in distinction to the fact that the universe is expanding, going outward.
Okay, yeah, our universe is expanding outward, right? So if we were to look at, if we just were to put 2 points, two little boxes next to each other in space and watch the universe grow over time, those boxes would move apart, right?
This is
Yeah.
condensing.
Yeah, actually, so one thing I want to just clarify here. So nothing's really moving in this picture so much as if I'm sitting in here, I have to keep on going in. And if you're sitting out here, then you have your choice. You can go out this way or you can go out. You can go in this way. But once I'm past this line, time going forward means I go deeper. There is actually a really interesting thing about the expansion of the universe, and since you brought it up, I want to just delve into that a little more. The universe is expanding so fast now that there are points on opposite ends of the universe that are moving apart faster than light. And that's a bit of a complicated statement. I know you think nothing can go faster than light, and there's sort of conditions on that. But what I do want to make clear about this is that means that as the universe keeps expanding, there are points which leave each other's universes forever. If I'm at one end of the universe and you're at the other, we wait a little while, the universe expands, we'll never be able to meet again. We've become separated by so much that even if we move at the speed of light, we will never reach each other. Yeah?
So then how do we know that there's an edge to the universe?
Oh, we don't.
That there's other things that we can't see that are...
Oh, yes. No, absolutely. This is absolutely the case. The universe is expanding so fast that things are actually leaving our horizon now. So there's actually no there's no evidence to suggest the universe has an edge. In fact, all our data suggests the universe just is going on forever, to the extent we can measure. Yeah.
The diagram of the 14 billion years from the Big Bang is in a tunnel shape or a hose shape, and it should be a sprinkler shape.
Yeah,
Because it's all directions, it's not just a tunnel.
Oh, that's absolutely right. I'm so glad that you brought that up. So I won't flip back to it just because I'm gonna, I don't want to find where we are again. But that picture, remember, that starts out like this and then kind of funnels outwards?
Yeah.
That's just looking, it's like looking at one little slice of the universe through time. And you're absolutely right. The universe is expanding out in every direction. In fact, sometimes people ask, like, where is the center of the universe? Like, where did the Big Bang happen? And because geometry in cosmology is a little bit weird, the answer is everywhere. Yeah, I know, it sounds weird, but the universe, a better picture would be to think about it like a surface of a balloon. The balloon is expanding, right?
In all directions.
In all directions. The surface of the balloon doesn't have a center. The universe, similarly, has no center.
As long as the balloon represents space itself. Right?
That's right, yeah. So here the idea is the balloon, the surface of the balloon is two-dimensional, right? So you gotta bend your mind a little bit to blow that up to 3 dimensions. But yeah, when I was a kid, I used to ask, where did the Big Bang happen? And my dad would say, oh, it happened in the living room. And technically he was correct. I just want to throw that out there. All right. Let's get back to our black hole picture here. Yeah?
So we have, not only do we have event horizons around the black hole, but we have an event horizon due to the expansion of the universe.
In a sense.
Yes.
Yes.
Now what happens if you have a black hole so massive, so large, that the celestial radius event horizon approaches and becomes equal to the universe expansion event horizon?
Well, there are some reasons why that wouldn't happen. Because if that happened, well, first of all, our observable universe would be full of it. Yeah, I mean, if that happened, if you had a gigantic black hole, let's see, let's delve into your question a little more. What would we be looking for? What would we see?
Well, so what happens? Do both event horizons cancel each other out?
Oh, good. Okay, so the thing that we gotta remember about the observable universe, and this is actually one of the ways in which it is different from a black hole. So when I say that we have a horizon around us, we have an observable universe, that is something that actually kind of travels with us. All right. So if I'm sitting over here, my observable universe corresponds to some giant sphere around me. But if you are sitting way on the other end of the universe, you have a big sphere around you, and that takes you to places that I can't get to. So everybody has their own horizon. It's not like an actual special boundary in space-time. It's just kind of how far I can see out, how far I can get to. Does that make sense?
So what happens if we have a huge black hole, and so that the event horizon corresponds to your event horizon looking into space in some weird sense? What happens if a black hole just becomes bigger and bigger and bigger and bigger till two scales become equal?
Well, in order for those two things to actually be equal, you'd have to be at the exact center of that black hole. Because, again, your horizon is centered around you. You are the center of your own universe. But the horizon that you have cosmologically, your universe horizon, that's not really a boundary in space-time in the same way as it is for a black hole. For a black hole, there really is some geometry that's specific to the black hole, whereas for the universe, it's just more to do with where you are in the universe. So it's not like there would be any particular spatial feature that would occur because of that. All right, so let's move on to two recent developments in black hole physics, because if you've been paying attention to the news, this has been a really exciting time for astrophysics. So on the left-hand side, you probably saw this image, or a less blurry version of it, a lot over the last couple of months. This is our very first image of an actual black hole. Before this, everything that we knew about black holes came from other observations, from indirect measurements, from theory. This is our first actual picture of one. So that's really cool. And on the right-hand side here, this is an artist's depiction, but still very, very significant. Just in the last few years, we had our first observation of gravitational waves from merging black holes. And that's actually an incredibly valuable tool for understanding both black holes, but also the universe at large and what else is in it. So I want to take a little bit of time to go through what's on the right-hand side of this picture, okay? Let's talk about it. So, what is this measurement? What is a gravitational wave? Let's start with that. So gravity is curvature of space-time, right? Now, if I imagine space-time as something that's kind of alive, something that's dynamical, something that can move and bend and curve, well, it stands to reason if I hit it just right, I can make a kind of a ripple in that space-time. I can make a wave that propagates through space-time itself. And that's what a gravitational wave is. So, here, this little drawing, this is one of our detectors, one of the LIGO detectors. And what LIGO does is it measures these gravitational waves as they pass through the detector. Let me show you how. So a gravitational wave comes through. What does that actually translate to? What does that look like? Well, a gravitational wave is a stretching back and forth of space as we see it. So when a gravitational wave passes along the detector, the length of the two arms actually change a tiny, tiny little bit. There's a laser beam running through each arm, so we can measure the length of each of those arms extremely precisely. And when a gravitational wave passes through, the length of the arms changes just a little bit, and we can measure that. Here's the thing. To do this experiment, you have to be incredibly precise. So let's try another guessing game here. To just quantify how precise this experiment is, let's say that I measure the distance from here to Alpha Centauri, which is the nearest star over. It's about 4 light years. The precision of this measurement, anyone want to take a guess at how that would correspond to the distance between us and Alpha Centauri? How precisely would I have to measure that distance to the next star over to get as precise as LIGO? To within a mile? Within a meter? What do you guys think? Molecule? You're not so far off. It's about a human hair. So imagine measuring the width of the human hair over the distance between us and Alpha Centauri. That's how good a job LIGO is doing. That's incredible. That's something that we could never do before. There's a lot of development that's gone into making this experiment actually work. Now, LIGO can see black holes when they collide together because that's an extreme event. You're really hitting space-time hard. So you're sending out a huge amount of gravitational waves, a huge amount of gravitational radiation. And that's been passing through us this whole time without us noticing because it's just such a tiny, tiny, tiny little stretching of space. But LIGO can see it. By the way, for reference, each one of these arms is about 1 kilometer long. Okay.
It's more impressive to point out that the change that they measure is the 1,000th diameter of a proton.
Yeah, so that's actually a really interesting part of the experiment because you have to measure the distance between the laser and the mirror, because there's a mirror at the end of that tunnel, to less than the diameter of a proton. And you kind of think, how do you possibly do that? I mean, the mirror has protons on it, right? Like if I have one proton out of place, that's going to disrupt my measurement? There is actually an answer to this question. A good answer about how we can measure around that. Anyone have any thoughts? Any engineers in the room?
Well, a single proton isn't going to affect the reflection of light. It's the averaging over a wavelength scale.
Okay, there's some averaging that helps us out. There's another really important part, and for anyone for whom the word is meaningful, the key word here is Fourier transform. So we can look at just particular frequencies. Because if there's something wrong with the mirror, say there's a defect or something, well, it's just going to be sitting there. It's not going to be moving back and forth at the same rate at which a gravitational wave is passing through the detector. So LIGO is designed to look for very particular frequencies of gravitational waves. And at those frequencies, you can pick out and say, oh, it's moving back and forth like this. I got it. It's a gravitational wave. All right. So what can LIGO actually see using this technology? Well, one thing it can see is merging black holes. Another thing it can see, I heard neutron stars before. We recently observed the first, and this picture is very blurry here, but these are 2 neutron stars smashing into each other. We observed that for the first time just recently. And that's actually incredibly cool because that's how some of the heaviest elements in the universe are made. So, okay, this is made of gold, right? Gold is, most of these really heavy elements are basically only made in this kind of a process. We just saw that for the first time. So that's kind of exciting. Yeah.
I have a mental picture of these neutron stars merging and splashing out droplets of neutron matter, which of course are now too small to exist as such. So they're going to be decaying, producing heavy elements from the top down rather than from the bottom up as in stellar nucleosynthesis. Have we detected any really heavy elements, like above uranium, way up?
I don't know the details of what we've actually confirmed about the elements produced in a neutron star merger. We have done electromagnetic follow-up of the neutron star merger that we have seen, but the thing is that the actual theory here is part of the problem, because we don't really understand how neutron stars behave in their interior. This is something that's very hard for us to study, and we are just getting the first data in the form of these measurements. So things like that, things like how this process of nucleosynthesis works in neutron stars. That's still a very active area of research. Yeah,
Just to clarify about gravitational waves.
by all means.
So, there are different lengths of gravitational waves?
Yeah, so the most important thing for us to think about tonight is different frequencies or different wavelengths of gravitational waves. And one way to think about this, maybe the simplest way, is that as these black holes here are spiraling together, think about them kind of pushing out one ripple every time they go around. It's not quite precise, but it does a pretty good job of explaining how frequently they send out these wave fronts. So when these black holes merge together, if they're circling around each other about 100 times a second, we will see about 100 wave fronts per second. So that's about the frequency that we see, yeah?
What is the typical frequency range?
It's about there, yeah. It's several hundred hertz, a couple hundred hertz. Yeah, so that's for these kinds of black holes, yeah?
So the higher the frequency, the stronger the gravitational pull?
So frequency really corresponds to how quickly these things are moving around when they smash into each other. And that is not necessarily tied to the strength of the gravitational wave. So actually, in a little while, we'll talk about some other systems that emit gravitational waves at different frequencies. And a really good example of this are supermassive black holes. So black holes that live like at the center of galaxies. They're enormous. They move around each other a lot more slowly. So LIGO actually cannot see supermassive black holes merging. The gravitational waves are too low frequency for LIGO to hear. It's a really good question. Yeah?
Just to be a little bit fussy though.
Please.
Isn't the radiation frequency twice the mechanical rotation frequency?
Yes, it is. So like I said, it's a little bit imprecise to imagine that I'm sending out those wave fronts.
And
Yeah.
all this rotation is clockwise.
I don't think that this is just an artist's impression here. So this isn't an actual astrophysics picture
Just
here.
depends on where you are.
Yeah.
They'll be running some clockwise, some counterclockwise.
Yeah.
Why?
Depends on what side.
So actually, this is actually a really interesting question. So whether the rotation is clockwise or counterclockwise, it does kind of depend on where you're looking at it from. So it kind of is randomly oriented. But there's a really interesting associated question, which is the black holes themselves. They're spinning like tops. Are they spinning the same direction, or are they spinning opposite directions, or is it random? That question turns out to have really serious implications, because it will actually tell us, we think, about where these black holes came from, how they were made. So I want you to hold on to that thought. We'll get there. But indeed, the alignment or anti-alignment of the black hole's spins can tell us some really interesting information. Yeah.
So can you tell what activity is going on by the frequency of the gravitational waves?
Yeah, so the gravitational waves tell us a whole lot about what made them. So the first thing that we can tell is what the actual sizes of the black holes are. So we can measure the mass of that system really precisely. We can say, we had two black holes, one was 30 solar masses and one was 28 solar masses. A solar mass is the sun's mass. And then they came together and formed a bigger black hole that had 54 solar masses of mass, let's say. That math doesn't quite work out, does it? Why not? 30 plus 28 does not equal 54.
Calling something else.
Radiation loss.
Radiation loss, yeah. So when two black holes collide, they emit so much gravitational radiation that it actually carries away a lot of mass. And that's a lot of mass, okay? We're talking about whole solar masses. The same energy that's in all the mass in the sun, E equals mc squared, right? All that energy, imagine several times that emitted in gravitational waves. That's why we can hear these things with LIGO, because they're just extremely loud. They are so energetic. They're the bright. If you think about gravitational waves as being kind of like light, we're doing astronomy with gravitational waves instead of electromagnetic waves. Those gravity waves are just, for that moment, they're the brightest thing in the universe. They're just incredibly loud. Yeah.
Do those rays travel as fast as light?
Oh, yes. Okay. This is another really interesting question. So, according to all our best theoretical understanding, gravitational waves should travel at exactly the speed of light. But remember all that stuff I talked about before with modifying gravity, trying to explain dark matter? One of the things that tends to spoil is that relationship between the speed of light and the speed of gravity. So LIGO is actually our best test so far of that fact that the speed of light is the same as the speed of gravity. How do we know that? Because we measured these gravitational waves from this neutron star collision, and we also saw a flash of light from the neutron star collision.
Yeah.
And because those arrived at about the same time, even though they've been traveling for billions of years, we can say very precisely that those two speeds are very close together. And that actually rules out a lot of the models people use to explain, to try to modify gravity. That's a really important fact. Yes?
What do we know, if anything, about particles that would be carrying that mass off?
But the particles that carry away that gravitational radiation.
Is this the mysterious gravitron we're
Oh,
talking
right,
about?
yeah. Good. So we're going to talk a little more about this later, but yeah, so let's think for a moment about light. Light is a wave. What kind of wave is light? Light is an electromagnetic wave. Okay. But you may have also heard about light in the sense of photons. Photons that are particles. So this is one of the weird things about quantum mechanics, that light is both a wave and a particle, this wave-particle duality. So the partner of a gravitational wave, its particle version, we call that a graviton. But the thing is, for reasons that we'll talk about in a minute, we basically have no hope of directly seeing gravitons, at least at this point in human history. And it comes back to gravity being really, really weak. So whenever we see a gravitational wave, that's just an unimaginable number of photons in some sense. Sorry, not photons, gravitons. But we don't actually have a great theory for how gravitons should behave. It's actually one of the major frontiers in physics right now. We'll talk about that in a bit. You guys are a great group. I just want to say, okay.
A comment on your earlier statement.
Please.
Actually, the flash of light from the neutron star merger is somewhat delayed.
It is, yes.
And I
So
don't remember how much, but the intergalactic medium does delay the light.
good, yeah. So there's actually several astrophysical processes that can delay the light. And one of the things that really helps us here is the fact that binary is so far away. So the fact that there was a small delay, but over billions of light years, is telling us that still, as a matter of alignment between those two speeds, they still have to be almost exactly the same, even if there's a little astrophysical delay that's hampering the light and not the gravity. Yeah?
So if, for example, an event that sends out gravitational waves, or light waves, or both, can be affected by a large mass of like a black hole bending that light, or can gravitational waves also be bent by a massive object, like a large black hole? Like that?
Yeah, okay. So again, this is all about the bending of space-time,
Yeah.
right? So basically everything follows its path forward in time. A gravitational lens, which is the kind of thing you're talking about, that's bending the path forward for everything. So yes, basically, everything will follow that curved trajectory around a massive object.
Another thing, if that gravitational wave that was first to be detected, had it been instead visible light, you would have produced a visible flash.
Had it instead been, you mean in terms of
If
energy?
If that energy had been in the form of visible light, you would have seen a flash.
I'm pretty sure you would have, just because of the enormous magnitude of that energy. I don't know off the top of my head how bright it would be. We can calculate that. The thing is that gravitational waves behave a little differently from light waves as they propagate, because we're measuring something that doesn't die off as quickly with distance. So we're in some sense we're actually a little bit advantaged with measuring gravitational waves as compared with photons. So it's a little bit tricky to on the back of the envelope to say exactly how bright it would have been, but I suspect it would have been. I mean, it's an enormous amount of energy.
We know the power flux, 3 solar masses.
Right. So if you know the distance, you can calculate the luminosity of that event. Yeah. Okay, question? Yeah.
Is there any way we might be able to discover how steady state or real accurate time is affected by gravity?
How time is affected by gravity? Yeah. So like we said, right? Gravity is curvature of space-time, right? That means it affects time, and this is actually something that we're now pretty good at measuring. And this is really not so much a question of measuring space as it is a question of measuring time. And we are now very good at building extremely precise clocks. We are, in fact, now so good at building these clocks that if you put one atomic clock here on the floor, and you put another atomic clock here on the desk, you can now measure how they tick at different rates because they're at different distances from Earth's center. That's how precise it's gotten. Yeah, that's a really exciting piece of science. Okay. Now, real quick, I want to just talk a little bit about what we can do with gravitational waves in the future, gravitational waves that LIGO cannot see. And I want to take us back to the very beginning of the universe, to the period right after the Big Bang that we call inflation, and the subsequent period before the development of this afterglow. See, almost everything that we know about the universe comes to us in the form of photons, light, that came either from the stars in the middle or from this afterglow itself. We can't see any light before that afterglow. And that's why we can't really learn about the universe before that happened, about 370,000 years after the Big Bang. We have to kind of model and guess a little bit. We have some ways, but it's tricky. But gravitational waves, they don't get hampered by that barrier. So if you can measure gravitational waves from the extremely early universe, think about them like stretch marks of the universe's birth, then you can actually learn about the conditions of the extremely early universe. So that's one thing that we're trying to do. That's not something that LIGO can measure, but there are other ways of getting at it. So this here is a picture, it's the sky map of the cosmic microwave background of this afterglow image here. If those stretch marks are in there, they'll show up as really subtle ripples in this kind of picture. So right now, one of the things that people are trying to do is get extremely precise measurements of certain patches of this little picture to see if they can see those ripples. And you know, there was actually a bit of a kerfuffle about this 5 years ago or so, where they thought they found them, and they published it, and it was in the news, and then they were like, oops, we forgot to correct for dust. So they had to retract that, and it was disappointing, but it's something people are still trying to do. And there are other things, other sources of gravitational waves that you could hope to observe from the very early universe as well that LIGO is not presently able to see. So there is definitely a long future ahead of us. We have, to this point, been studying the universe entirely in terms of light, entirely in terms of electromagnetic waves. This is the first time that we actually are able to study it in some other kind of spectrum, gravitational waves. So this gravitational wave astronomy is really the future for us right now.
Is there a cosmic gravitational wave background?
Yes, we think there is. The question is whether we're going to be able to observe it. And the other question is what are the things that might produce one? So there are things like in the very early universe, as the universe basically as it cooled down and as some particle physics changed shape as the universe got cooler, those processes may have emitted gravitational waves that would comprise such a background that we could see today. So that's one of the things that we're very interested to look for. And LIGO is already putting limits on that background of gravitational waves.
Shouldn't it be about the same energy density as the electromagnetic background?
Oh, well, that depends. It depends on what produces the gravitational waves. The photons, we understand pretty well where those photons come from, how they were produced. The gravitational waves, the story's a little more murky. There are a lot of different physical processes that can produce gravitational waves that don't produce light and vice versa. So it's not necessary that they're really comparable.
Well, from the inflation, are you have it think there will be a thermal equilibrium at some tends to 32 Kelvin?
The thing is, though, that, okay, so just to clarify the question. So light that we have from that time, when the universe was really, really hot and really, really dense, all these different particles were in thermal equilibrium with each other, which means that basically it's a big soup of particles and antiparticles that are all kind of sharing all the energy. So using that model, you can predict very precisely things like how many photons you should get out of that thermal soup. The thing is, that thermal soup actually formed after inflation. So there's a period that's not shown on this diagram that we call reheating after inflation, when all that energy from inflation then got dumped into everything else that we have around us. So if there are gravitational waves that are produced from the inflation process itself, those are not necessarily connected to the thermal processes that give us the rest of stuff in the universe. That's a really good question. Okay, now occasionally when I talk to people about black holes, I get this question: are black holes going to swallow us? And you know, sometimes, you know, once I thought I was doing so well explaining something to somebody about the black hole picture that came out, and then he was like, I'm really glad that we have this picture, because now we know, and now we have our defense against black holes. And I was like, oh no. Let's slow down. So the answer to this question is no. And the reason for that, I don't have to give you any theoretical backing for why this is the case. The simple answer I can give you is the Earth is about 4.5 billion years old, and it hasn't been eaten by a black hole yet. All right. So for the rest of this evening, you could put this possibility out of your mind. Okay. Now, actually, as long as we're talking about this, I do want to. Did you guys hear back maybe 10 years ago worries about how the LHC was going to make black holes that were going to swallow the Earth? Who heard that in the news or something? Oh yeah, it got around. So you heard it too. So the worry here was the LHC is going to, explore some new energy, some new physics that's going to make a tiny black hole. That black hole is going to grow out of control, and it's going to swallow the Earth. Again, let me back up here. Again, no. The LHC is nowhere near, first of all, the energy that we think you would need to create a black hole. And second, if you did create a black hole at those energies, if you do that, then Earth has already been bombarded with those black holes for a long time. Because the LHC, it's nice for us because we can actually look at these collisions in a tunnel where we have instruments, but there are other particles at much higher energies that hit the Earth all the time. There are these things we call cosmic rays, these really, really high energy particles that zoom into us from outer space. Those are way, way higher energy than anything we can make at the LHC. So if those collisions make black holes, they've been doing it for a very long time. All right, now with that out of the way, now let's back up a little bit and talk about some of the history around black hole theory. Because black holes have been theorists' favorite toy for a very long time. And one of the major contributors to that has been this gentleman here, Stephen Hawking. And I'm borrowing his slide here to make the point that black holes aren't so black after all. So let me walk you through one of the first major developments around black hole theory, one of the first really surprising things we learned about that. And that's that even though once you enter a black hole, you can't escape, that doesn't mean nothing's coming out of it. So what I want you to do is to take a kind of an imaginative leap here and pretend that you're in a vacuum. Okay. A vacuum has nothing in it, right? Okay, all right, yeah. Well, there's one little issue here. You gotta think about the vacuum as something a little more than just nothing. We think about the vacuum as, this is an imprecise kind of analogy, but think about it as being full of little tiny pairs of particles that keep on popping into existence and meeting up each other and disappearing. We call these virtual particle pairs. Now, here's the thing about these virtual particle pairs. They're very short-lived. They kind of borrow a little bit of, they don't really borrow energy, but they are these extremely short-lived little excitations in the vacuum. Now, here's the thing. Say we have a black hole, which is right now represented by this cylindrical diagram. And let's say one of these pairs of particles that's popping up and coming together, let's say it happens to form really near the black hole's event horizon. And then one of the two particles enters the black hole horizon, and the other one doesn't. This particle here can't find its partner again. So it can't pop back into non-existence. So its only choice is to become a real particle. Is physics fun? So what happens in this case is that particle escapes to infinity, And now that particle is a real particle, meaning it has energy. Where did that energy come from? The only way that the energy could have come from somewhere is if it came from the black hole itself. So this is a process that we call Hawking evaporation, or Hawking radiation, as you might have heard of. And the idea is that a black hole that has very, very strong gravity at its surface will basically be breaking down the vacuum around it and emitting a bunch of particles. Now, here's the really weird part about this evaporation process. The thing is, first of all, it gets stronger the smaller the black hole is. A little weird. Why should that be? Here's surface. Okay, yeah.
Surface gravity.
Yeah, surface gravity, exactly. So black holes have this kind of weird property that they're everything that you could want to know about a black hole is determined basically by its mass. Let's say it's not rotating or charged right now. So if I tell you what the mass of a black hole is, I've also told you how big it is physically. Okay, and it turns out that if I keep on dumping matter into a black hole, the radius of the black hole is directly proportional to its mass. Yes?
Why are you shaping a black hole like a barrel instead of an orange?
You mean over here?
Yeah.
This is a kind of a diagram that we draw to look at the actual space-time.
It skews your understanding. The drawing gives you unassuming ideas.
Yeah, so this drawing is actually a kind of a mathematically precise diagram we call a Penrose diagram. It's a way of mapping, just so while we do theoretical calculations about what different regions of space-time are accessible to each other. So we're not thinking about this as a literal picture, we're really thinking about this as a calculational tool. So this is the diagram that Stephen Hawking chose to represent this to an audience, which probably isn't the one I would have chosen, but I chose it, so there's that.
Well, the vertical is supposed to be time, isn't it?
Yeah, so this diagram, this kind of diagram is one way of representing different regions of space-time. So yeah, you basically choose, like, here's basically a time axis, here's a space axis, here's a line you can't cross, there's an event horizon, there's a singularity at the end of that line. Things like this, these are all features of the diagram, but they're not meant to be, literally representative of like the shape of a black hole.
And the singularity lies to the future. The wiggly little line itself.
Yes,
is
it
not the
lies to the
singularity.
future. So the idea is once you're in the black hole, all paths lead to the singularity. That's exactly the idea. All right, let's get back to the idea of Hawking radiation. So I was just saying that if I dump more matter into a black hole, its radius, its size, is proportional to how much mass I throw into it. Which is a little weird because if I have a ball and I fill that ball full of something, its volume is actually proportional to the radius cubed, right? So as I make that black hole bigger and bigger and bigger, it's actually getting less and less and less dense. Actually, like the black hole that we took a picture of, the black hole that picture that's been going around, the average density of that black hole is like the density of air. It's really not very dense. It's a huge amount of space. So, now once we know about that mass, we know everything about it, right? So we have a small black hole. It's going to emit more Hawking radiation. This is a problem for us because we don't have any small black holes. All our black holes are really, really big. And that means we have not been able to see any Hawking radiation. We have never been able to see one from a real black hole. The Hawking radiation that a star-sized black hole emits is way, 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 way too low luminosity, too low energy for us to see.
10 to the minus 7 Kelvin for a solar mass black.
That's roughly right, yeah. Yes?
Wouldn't also, basically the same proportion of antimatter versus matter particles that would be created through that process and eventually annihilating each other? So maybe that's why you wouldn't see them?
Okay, we're about to talk about something very related to that. So the thing is, if we had antimatter and matter, meeting each other outside a black hole, we'd still be able to see other things that they annihilate into. So that wouldn't hurt us. But there's a very related question. which is, if we have equal parts matter and antimatter coming out of that black hole, but I only threw in matter, there's some information that's been lost, or so it seems. This process of evaporation seems kind of random. I have some pair of particles that pops into existence near the black hole, and they carry away whatever they happen to be at that one moment. There's no record of what I threw into the black hole. So you can imagine I have a little black hole, it evaporates, loses mass, shrinks. It actually kind of explodes as it gets down to really low masses, and then it's gone. And what am I left with? I'm left with no trace of what I threw in, only random thermal noise. This is very disturbing to modern physicists, because we know the laws of quantum mechanics tell us everything that we do ought to be reversible. You shouldn't be able to lose information this way. And black holes seem to violate that principle. So studying black holes actually has really kicked up the game in terms of understanding how quantum mechanics and gravity play along. And we still don't know a lot about this. There's a lot of research into what this actually entails. String theory is really an outgrowth of this question. How do we have a theory of gravity that is also quantum mechanically compatible? There's a bunch of people who have been some of the biggest figures in string theory. But ultimately, we do not really know experimentally how black holes and how really strong gravity behave quantum mechanically. So black holes, being able to observe black holes and looking for new phenomena around black holes is one of the most important things we can do if we want to understand gravity in more extreme circumstances. And one of the things that LIGO has actually done for us is actually confirmed that, at least so far as we can tell, as far as we can probe, general relativity isn't breaking down and yielding to some new replacement theory. So it seems like, as far as we can tell, this theory is working really, really well up to really, really strong, stronger and stronger gravity. All right. Now, I want to turn to the latest craze in black hole theory. You guys ready? We have all this dark matter floating around, right? Now, I've told you some things about dark matter. It doesn't emit light. It doesn't reflect light. It just kind of floats around, acting only through gravity. Could be black holes. So this is actually an idea that's been gaining a little bit of traction lately. The idea was, right around the time when we first detected gravitational waves from the black hole, from the black hole merger, people realized that the same kind of masses that we were seeing in that LIGO observation are kind of hard to get from stars, kind of hard to make through astrophysics, but there are some really easy ways to make them.
The library closes in 20 minutes. If you need a library card, please go to the service desk now. The restrooms will be locked 10 minutes before closing. If you need to print or make copies, please do so now. La biblioteca cerrará en 20 minutos. Si necesitas una tarjeta de biblioteca, por favor visite el escritorio de servicio ahora. Los baños estarán cerrados en 10 minutos. Si necesitas imprimir o hacer copias, por favor hazlo ahora.
Okay, so here's what I want to do with our 20 minutes. Okay, I want to go on a couple of really brief deep dives into some things that we've really recently learned about the possibility that dark matter might be made of black holes. Okay, so I'm going to take maybe 10 minutes to do that. And the rest of the time I want to reserve for you guys to ask whatever's left on your mind, okay? Anything right now that you're going to be really sad if you don't ask before we leave tonight? Okay. So what I want to just point out here is that if black holes form from supernovas, from stars dying and collapsing, well, then there's no way that those black holes could be dark matter, because dark matter was around before stars were around. So we can't do that. If we want black holes to be dark matter, we need some other way for them to form. Fortunately, we've got a way for that to happen. Let's go back to the very early universe. And let's say that in the very early universe, we had our soup of stuff. And let's say that there happened to be some regions that were really, really dense compared to others. what if those regions just collapsed? Just collapsed all the way into black holes. We know that could happen. We have a lot of theory that tells us we can produce these black holes in the early universe and still have them around today in the form of dark matter. We call these primordial black holes. And as far as we can tell, some or all of dark matter could be made of those primordial black holes. Yes?
So if we got a recent photograph of a black hole and we can't see dark matter, how would a black hole be made of dark matter?
So really in this case what we're saying is dark matter wouldn't actually be a new particle. Dark matter might actually just be black holes, lots of them. So the idea here is that you just have way more black holes than we thought before because you can't really see them, right? You can only tell they're there from gravitational waves when they happen to collide with each other. So it's possible that we don't actually have a new particle. This is one of the alternatives. You can think about a black hole as being a very heavy particle in some sense.
I don't think that's what she was saying. What we are shown as this is a picture of a black hole. It's
Yeah.
not just like you could see this with your eyes if you were really big or whatever.
So the picture that you're seeing, yeah, I mean it's not quite if you were seeing it with your own eyes. It's really radio, but it's still light that we're seeing in that picture. But we're seeing a shadow where there's no light coming there because there's a black hole. Is that what you're getting at, or something else?
It's gas swirling around the black hole.
Yeah,
Radiation.
exactly. The gas is very hot, so it's emitting a lot of radio waves.
Is it so hot that it would emit visible light were it not for the gravitational redshift?
So there is visible light being produced there. The reason that we're not looking at it is actually because it's actually easier for us to observe those radio waves because of atmospheric filtration. So if you want to do a measurement like this, and you have a lot of ground-based telescopes, you want to be looking at a wavelength that you can see through all the water in the atmosphere. Okay, so real quick, what kinds of black holes could actually work for this purpose? It actually can't be the really big ones, the supermassive ones. Those are too big, they're too bright because of exactly this, all that gas. It can't be the really small ones because they radiate too much, they Hawking evaporate away and they're gone. And it can't be ones that are like, say, Earth mass, as far as we know, because those bend light too much. If there would be just too many of them, we would have seen them already. So now what I want to do is just take a look at 3 different scenarios really briefly. One in which all dark matter is made of black holes. One in which, we'll probably skip B. We'll probably go straight to C. So let's say either all dark matter is black holes or there are no primordial black holes. All black holes are made from dying stars, and then we have to just learn about dark matter in some other way using its relationship with black holes, okay? So let's start with A here. Let's start with what we can learn if all dark matter is actually black holes and there's no new particle. So here, I want to walk you through one scenario. There's a lot of scenarios, but one of the ones that I've worked on. And that's the case in which you do actually have these really small black holes, which I just said couldn't make up all of dark matter. So am I lying to you guys? Well, the catch is they can't make up all of dark matter if they actually evaporate away and are gone. But remember, we had this paradox about information being lost. One of the possible resolutions to that paradox is that when these things get really small, they actually stop evaporating. And you have a little relic, or a little tiny microscopic remnant of a black hole. And those tiny black holes could still be dark matter. So just to put this in context here, I want to show you how tiny I'm talking, okay? So these tiny relic black holes, we think they would weigh about as much as a grain of sand each. But remember, black holes are really dense, right? So even if they weigh as much as a grain of sand, they're not as big as a grain of sand. In fact, they are so tiny that comparing a grain of sand to one of these black holes is like comparing the entire observable universe to one grain of sand. That's ridiculous, right? Yes?
They're smaller than a Planck length?
They are about a Planck length, yeah. So how are we going to find these things if they're out there? They're way, way too small to be sucking up matter. They're not going to destroy the Earth, right? And the thing is, if they have some electric charge, if they have some electromagnetic interactions, then maybe we can actually feel their forces. Because again, electromagnetism and all the other forces are way stronger than gravity, right? So here's the idea. What we did is took a look at the situation and said, is there a way that we could have these things be charged? We have an idea. When black holes radiate, when they evaporate, we had a comment a little while ago, they can evaporate not just into light, not just into matter, but also into antimatter, all kinds of things, right? Well, they can also evaporate into charged particles. So a black hole, a tiny black hole, can emit, say, an electron and an anti-electron with positive and negative charges. And if the black hole swallows the anti-electron and sends the electron flying, well, that means it has to gain that charge. So if these black holes are emitting all these charged particles as they go down to their final destination, then we can expect them to retain that little bit of charge. And then what you have at the end of the day is a bunch of little black holes that all have electric charges on them. And those we can see. Those, if they pass through a detector, they'll bump into an electron, they'll send it flying, and we'll be able to see that in a detector. We'll see a track, a straight track, a kind of a trail of junk, a trail of destruction as a black hole passes through our detector. The only catch is, compared to particles, these black holes are really heavy, so they'd be quite rare. So if you want to catch one, say you wanted to catch one passing through the screen. Any guesses about how long we would have to wait to see one? A day? A week? 2 months? It's pretty close. It's about a year. We'd have to wait about a year to see one black hole come through this screen. All right, so we need not a sensitive detector like we usually use to look for dark matter. We need a big detector. And we think that we can actually do this really soon. So there are other detectors that aren't really made to look for dark matter. They're made to look for things like neutrinos. So those aren't so much sensitive as they are really, really big. And the thing is, because these things are such a clear target, we've shown actually that if you have a big neutrino detector, you can detect these if they make up dark matter. So that's one of the ways that we can look for primordial black holes in the form of dark matter. Since we're running a little low on time here, I think I definitely want to skip B, and I will kind of swoop forward to C here, but I'm actually going to pause here in case anybody has any questions they want to ask. We don't have to go through C here, so this is a great time to ask some questions, please.
I really should have butted in and asked this question when you showed the diagram early, but the MO of people interrupting you to ask questions hadn't gotten established yet.
Now's your moment.
It was the circular diagram with the three pie.
The pie chart? Yeah.
The yellow, the green, and the purple, and we and everything we see is the purple.
That's right.
And the green, which was like a quarter of was dark matter, and more or less 3/4 was the energy.
Yes.
And I remember asking this question when I first heard about dark energy, and I don't remember what the answer was. But I assumed it was that pi represents the mass, because it obviously doesn't represent the space, because the dark energy would occupy 99% of the space.
Okay, yeah, very good. So in fact, all of these things sort of coexist in the same space. So something I probably should have said actually is that dark matter.
But what proportion? Since that's what you're representing.
Yeah. So dark energy actually we're pretty confident is extremely uniform throughout space. There's dark energy here. There's dark energy here. There's dark energy here. There's probably also dark matter here and here and here. Not if it's black holes, but if it's lighter than that, then yes. Dark energy is just a name we give to some energy that seems to be extremely uniform throughout space. We have some theoretical ideas about why it's there. We're not entirely sure about why it has the density that it has. I'm going to say it's relatively well understood compared to dark matter, just because we have a great idea about what it could be. But does that answer your question? I'm not sure.
No. The way the only way I was able to accept the concept that it represented 75% of the mass was that is based on E equals mc squared, and that meant this dark energy is not what we would think of as massive.
That's exactly right.
It's not heavy. We're not experiencing any mass from it. That maybe scientifically a tiny bit can be detected, but it's not like the obvious massiveness of the dark matter.
Yeah. So
if I finish the sentence.
Sure.
So that meant, so if it nonetheless represented 75% of the mass in the universe, that meant that there had to be astronomical amounts of it.
Exactly what there is. That's right. Because it's uniform throughout space, and space is huge.
Right.
That's why there's so much of it. If you look back to dark matter is all clumped up in smaller areas, right? So it's denser in those areas, but they're so much smaller. So you're exactly right. E equals mc squared is exactly the right way to think about it.
Now, is there any possibility, the ancient systems talked about earth, water, air, and ether. And is there any possibility that any of this would be analogous to, the ether in the Hindu system was the equivalent of space, so-called empty space.
Okay, so I'm not gonna, I don't, want to say anything about what the authors of that literature knew about, the properties of space or properties of vacuum. But what I will say is that you can absolutely think about dark energy as being energy that is associated with vacuum, associated with space itself. So if that's a picture that helps you to understand it, by all means, that's very right. Yes.
But a vacuum would collapse, right? It would fall in on itself.
It wouldn't actually. I'm going to defer to Diane on how much time we have for additional questions.
Like we have the library
Please
closes,
gather
so we're going to have to have
and make your
questions.
way to the exit.
Okay.
La biblioteca está cerrando. Por favor.
But you can catch me on my way out if you want to talk some more about it, okay?
Let's talk until they kick us out.
Okay. So at this point, so should we take a few more questions, or shall we clear the room? What's our need about?
No primordial black hole. What is your, just real quick.
Oh, real quick, what can we
let's
do?
have the 2-minute version.
Sure, let's get the 2-second version. So the idea here is that even if you don't have any primordial black holes, you can still learn about dark matter using black holes. And the idea is that dark matter can affect black holes in ways we can measure. So there are a bunch of different tacks people have taken on this problem. I'll just tell you in 30 seconds about one that I've worked on, which is that if dark matter particles bump into each other, that actually changes how they collect around black holes. So if you take a look at...
They'd have to be a particle though.
That's right. So if we're saying that there are no primordial black holes, then that means that dark matter has to be a new particle. So then we're thinking about the properties of that particle. Very good. So the fact that so it turns out, if you look at supermassive black holes, we expect to see those colliding. We haven't seen it yet. Now that could just mean that we're not quite at the place where we can see that yet. We don't have sensitivity to it yet. But it's also possible that they actually just don't merge, that they just kind of hang out and spiral each other for very, very, very long times. Now, one of the things that we've been able to show is that if dark matter particles can bump into each other, then that lets them basically be eaten up by the black hole in the same way that gas is, and that can help to drive two big black holes together. So what that means is if you can set a limit on how fast these giant black holes merge, you can actually learn about whether or how much these dark matter particles bump into each other, which is something that otherwise we really can't get at with any other traditional observation. That's the 30-second version. There are lots of other things that people do in this space. They're trying to figure out about the properties of dark matter using the behavior of black holes.
Well, yeah.